All right, this is one for day 1. Okay, if you want to, you could start with these notes and you could label them as a new chapter, right? If you want to call it chapter 1b. Kind of marks a little change for us that we're now looking at functions that are nonlinear. Okay, that'll take a while, but we'll at least start that process. And the one we'll do first is kind of the natural starting point, a quadratic, okay? You've probably seen them before. I know you've seen them before. They're pretty common, right? Typically, we just draw a picture of it, right? This graph has that parabola shape. Curved graph characterized by an x squared term. It can change direction one time. Okay, that's really all I'm going to say about graphs or show you, because we'll get to graph and quadratics. That's just really not going to be, that's not going to be today, okay? The standard form of an equation that's a quadratic looks like this. ax squared plus bx plus c. There's one rule, though. A can't be 0. It could be negative. It could be a fraction. Can't be 0. If it was, that first term would go away, and you'd be left with bx plus c, which that would be a line, right? It would be a line with a slope of b and a y-intercept of c, right? We usually call them m and b respectively, but whatever. You can call them whatever letter you want. It would be a line, not a quadratic. So to have that x squared term there, a can't be 0. All right, you'll see for a variety of reasons, okay, both in applications and graphing, we often on quadratics want to know where its x-intercepts or its zeros are. So typically, to find these zeros or x-intercepts, we set it equal to 0, and then we'll apply what we call the zero factor property. Now you might be thinking, what on earth is that? The zero factor property says this. If a times b equals 0, then we know one of two things. A was 0 or b was 0. But for their product of a times b to be 0, both numbers don't have to be 0, just 1, okay? Just 1. All right, now you'll see how that shows up here as I factor this. Here's a little common factoring. They both have a factor of 3x. After I take that out, I'm left with 2x minus 1, okay? So see how I split up this quadratic into 2 factors, okay? Because it's second power, there's always only going to be 2 that it would split up in, and you'd solve each of the factors equal to 0, okay? Well, what that property says is for 3x times 2x minus 1 to be 0, that means one of two things. Either that has to be 0, or that has to be 0, one or the other. But I divide both sides by 3 here. I get x equals 0. That would be one of my x-intercepts. Here I'll add 1. And then divide by 2. And the other would be x equals a half, okay? Now because it's a quadratic, you see the number 2 show up over and over again. When we're solving for these zeros, at most we could get 2. It's conceivable you could have a problem where it doesn't give you any. It's possible. In rare cases, you can get 1. Most cases you would get 2. It's impossible to get 3. So you'd expect when you're solving for zeros, most likely I'm looking for 2. Okay. Actually, we'll see in this case, we'll only have 1. All right, two factors of 16 that add up to 8. I'm going to be looking for 4 and 4. Everything is positive, right? Because it's plus 8x and plus 16. So it splits up into the two factors, but obviously it's the same factor. Subtracting 4 from both sides. You get x equals negative 4, which again, that can happen, right? It's possible to just get 1, okay? Same process though, right? But if you only get one solution, it kind of takes care of itself. They're like, oh, I factored it, but it's split up into two factors of x plus 4. Okay, I just need to solve x plus 4 equals 0. Be careful with this one over here. 2x squared plus 9x plus 4, right? Before I start this process, that really goes back to that zero factor property. If a and b times, equals 0, if a times b is 0, then a or b has to be 0. It's not the 3 factor property, right? I couldn't say that, if a times b equals 3, then either a is 3 or b is 3. It doesn't work that way at all, okay? This is kind of a unique situation with it being equal to 0. All right, we need to factor, but a isn't 1, so we'll use our guess and check method. Not too bad. Really running out of room over here. I need to look at factors of 4, which would be 2 and 2, or 4 and 1. To get a middle term of 9, I feel like I have to have a 4 in there somewhere. 2s aren't going to get it done. In fact, if I put the 4 here, that gets multiplied by 2. If I put the 1 there, that gets multiplied by 1, and we're good to go. Okay? Here we have 2 to solve because we have 2 factors, but it's not the same factor, so they will give us 2 solutions. Whoops. Getting a little ahead of myself. Let's see here, add 1. And x is 1/2. All right, there you go. That's plenty on finding your zeros, right? With factoring. And again, you'll see, hopefully, throughout this chapter, for the purposes of producing a graph and for solutions to application questions, a lot of times the x-intercepts or the zeros are kind of relevant. Right, they're 2 points on a quadratic graph that we want to know where they are. All right, so another method without factoring is called extracting square roots. Okay, notice the key there, without factoring, okay? No factoring needed on any of these, all right? So if you get something like this first one, to undo the square root, right? Because technically it is a quadratic. If I had wanted to, okay, so if you're looking at this, and you're like, hey, couldn't you just have followed the same rules and done that? Yeah, I'm not saying for all these that you couldn't potentially set it up to factor it. I'm saying that if you see them in these form, in this form, you don't need to. Okay, and it's probably easier to do it without. They're really all I have to do to get the solutions here is take a square root, and I get that the solutions are plus or minus 7, because the square root of 49 is 7. Okay? Same thing here. Divide both sides by 4. You'll get that. Square root, x is plus or minus. Now 3 is not a perfect square like 49, which is fine. I just say plus or minus the square root of 3. Okay? Start with the square root here, and we'll get x minus 1 is plus or minus the square root of 10. And then add 1, which would give us 2 solutions. You could have square root of 10 plus 1, or x could be negative square root 10 plus 1. Okay? So if you have a quadratic where you're trying to find the zeros and factoring doesn't work well, or it just doesn't seem to fit, don't forget about this possibility that you could try extracting square roots. And you could solve for those zeros without factoring. It's almost like you just take a straight algebra approach and you just solve it, right? This actually kind of would be our approach that we'd like to take, but it's really more that if you look back on the first slide, this wouldn't work with those first 3, okay? Just the fact that those had 3 terms in those equations, that it wouldn't work out. All right, one final way to find some x-intercepts is the old quadratic formula, okay? This would basically be like if what we saw in the first 2 slides, if those didn't work, this would be like your last resort, because it's a little tedious, but it always works. It's a real nice thing about it. Quadratic formula. All I have to do is know A, B, and C. As long as you know A, B, and C, right, you're good to go. Now here's the thing on this first one. I could go through and be like, oh, hey, I'm going to go try to factor this. And look, it's not going to work. But I'll spare you, right? You can try to factor that. The A is 1, so you could look for 2 factors of negative 9 that add up to 3. And then, you know, spoiler alert, you're going to be looking for a while because you're not going to find them. But that's okay. We have the quadratic formula, which says if A is 1, B is 3, C is negative 9. We plug those coefficients into this big, horrible-looking equation. Oh, it's not that bad. All right, opposite of B, plus or minus square root of B squared minus 4. A is 1. If you're having a hard time following along here, I'm using the formula up above. I've identified A, B, and C. They're all going where they belong. Okay. Cut this off right here to make sure I maintain room for my next problem. Now when I simplify, right, there's nothing to do with negative 3. I usually like to stay focused on the square root, okay? 3 squared is 9. It looks like basically 9 plus 36. (36) coming from negative 4 times negative 9, okay? I'll just check to see if I can simplify this, which I can. Right here, this 45, I could go square root 9 square root 5, right? Square root of 9 is 3. So this would lead us to our final answer of negative 3 plus or minus 3 square root 5, all divided by 2. And those would be your final answer, those two, okay? Typical case with the quadratic, it gave us two solutions. Now, when you see that, if you're like, hey, those answers aren't very nice, with the quadratic formula, that's usually the case. If the two zeros came out to be whole numbers or nice fractions, like, I don't know, a fourth, a half, a third, something like that, that typically means factoring would have worked, especially if the answers were whole numbers. That would have been a red flag that, hey, this could have been factored. If we're going to the quadratic formula, it means we have cases where, yeah, you know, they're going to be decimals or irrational numbers that have, you know, non-perfect squares, and that's okay. But that's, if you're using the quadratic formula, that's kind of what you should expect to get. All right, 3x squared plus 2x, right? Same as before, if we're going to start to solve for these two solutions, it has to be set equal to 0, okay? There's A, which is 3. There's B, which is 2. There's C, which is negative 10, okay? I was just thinking to myself, opposite of B. Okay, that's great. What is it? Oh yeah, negative 2. That's better. B squared minus 4. A is 3. Need to extend my square root here. All of that over 2 times 3. I like to double check right here, just to make sure everything's going okay, because if I've substituted something incorrectly, I'm doomed. So it's good to double check before we start to simplify. Is every single number exactly where it belongs in the formula? I think it is, okay? All right, nothing with the negative 2. Clean up the bottom to 6, right? And this is where, again, most of the action happens. What does that square root simplify to? Looks like it's 4 plus 120, right? 2 squared being 4. Negative 4 times 3 times negative 10 is 120. Certainly if you need to pause to crunch those numbers, but you should find that all comes out to be 124. But the only thing left is with 124, could I simplify that? And I can, because I can split up 124 to 4 and 31. That's going to be 2, but now check this out, okay? I have 3 terms. All right, one here, negative 2. This is really positive 2 and then positive 6. Those are all divisible by 2, so here's what I'm going to do for my final answer. Divide each of those by 2, so I'd have negative 1. When I divide this by 2, that's basically gone, and then I have the square root of 31, which can't be reduced, and then 6 divided by 2 would be 3. There's your final answer. Negative 1 plus or minus square root 31 over 3, okay? So if you do reduce what number is underneath the square root, what we would call simplifying the radical, see if that leads to a common factor between the 3 terms, right? In this case, I had negative 2, 2, and 6. Those were all divisible by 2, so I have my answer fully simplified. All right, one more. The form looks good. A is 2, B is negative 5, C is 5. All right, let's get it all set up. Again, this is a good place to pause. Make sure everything is shipshape. B squared. I'm literally checking mine as we speak here. I think I'm good, right? There's really never anything to simplify with B. The bottom's usually pretty simple. And then we always spend a lot of our time on the square root, but check out what happens here. Negative 5 squared is 25. Negative 4 times 2 times 5 is 40. And it seems like we kind of have an issue, right? We get the square root of a negative, okay? For now, okay, you are allowed to say no solutions. There's no solutions that we could express with real numbers, right? You may have seen at some point in the past the square root of a negative, we have to use imaginary or complex numbers to describe the solutions. Okay, we haven't gotten to that yet. We will in this chapter. We'll get to like how do we handle if we're solving and we get the square root of a negative. How do we deal with that? Okay, but we're not there yet. So for now, you can say no solutions on a graph. Here's what's happening: is this formula you're looking for the zeros or the 2 points that this graph would touch the x-axis. Something like this is going on. You have a quadratic that opens up, and its vertex sits above the x-axis, okay? End result, as far as like two real solutions where it touches that x-axis, we don't get any because it doesn't touch it, okay? But just keep in mind with this no solutions thing, in time that'll change, but for the purposes of section 4, right, you know, if on your homework assignment for 1-4 day 1, if you came across this, you're good to just stop and say, there's no solutions. Alrighty, that's all for 1-4 day 1. In the next couple days, we'll continue with quadratics.